have here with us is research director at ENRS Marseille, leading a team studying instabilities and turbulence, fluid, but also in plasma. He's been collaborating with Thierry Cadarache for more than 15 years now. Yeah. Sure. And so I had the pleasure to listen to both turbulence and rotating disk boundary layers and instability. So,
yeah, thank you, Yannick, for this nice introduction. So thank you all for attending this this conference after lunch and with these very hot temperatures. So yeah, today I will speak about stability and the transition to turbulence in rotating disk boundary layer. So for me, it's a rather hot topics. What I did with in collaboration with Jean-Marc Chaumas from École Polytechnique in Paris, Mathematics, and Bertrand Viau from the French Air Force School in Salon de Provence. This topic was recently renewed for me because I was invited to publish a review paper in the Philosophical Transaction of the Royal Society 2 years ago in the volume to celebrate the centenary of the seminal paper of Taylor, the 1923 paper of Taylor. So this talk will be closely inspired from this paper. So this is a view, experimental view of the rotating disk boundary layer from above. So you are disk rotating in the fluid at rest. What you can see, so it's the first. So this is the center of the cavity. This is of the disk. This is the radius. So you can see that there is, following the radius, an evolution of the Reynolds number. So the local parameter numbers, which are the Reynolds, which is function of R. And this is also a function of the Rossby number, which is the ratio between the Coriolis force and the linear advection curve. So you have the flow, which becomes more and more unstable when you go from the center to the external radius. And as you can see, there you have first the transition with instability under the form of spiral patterns, and rapidly followed by incipient turbulence. So this boundary layer, it's a rather hot topic in fluid mechanics. And the most famous paper is the Ekman paper. We did the name of the Ekman boundary layer in 1985. But this study was renewed in the 90s following the seminal papers by Lingwood. In fact, to observe that the transition between the laminar and stable flow and the turbulence was rather robust when you change experiments, and was relative. The Reynolds number between the transition to instability and the transition to turbulence was relatively close, suggesting the idea of a direct route of turbulence from unstable flow to turbulent flow. And so the questions which arise is, does local absolute instability trigger the onset of nonlinearity and then transition to turbulence? And does it exist a direct route to turbulence? And so for us, it was the beginning of interest, and this motivated intensive direct numerical simulations that we perform at M2P2.
So the question to this picture.
Yeah.
I don't understand, where's the disk?
So this is below.
Ah.
You have a fluid, a cube with a fluid above, which is at rest, and you start to make the disk in rotation. Okay, so I will come back in detail on the physics of the boundary layer. And so this is a view from the top. Okay. And yeah, I will come back. Okay, this is the outline of the talk. So I will explain the general context of the study, some words about the theoretical base flows. One of the interest of this boundary layer is that you can derive analytically similarity solutions, so that are very useful to be considered as a base flow for linear stability analysis. Then I will introduce a few words about instability theory, and then scenario to turbulence, and few remarks to conclude the talk. Rotating disk boundary layers, as you know, are relevant to many configurations, from geophysics to industrial applications. atmospheric and oceanic boundary layers with the role of the rotation of the Earth on pattern formation, development of currents, and also the impact of heat and mass transfer. So it's very important in the study of these boundary layers. But it's also very relevant with many industrial applications where you can have rotating cavities. And typically, the most clear application is turbo machinery, where engineers are interested in particular in the compressor part. But you are here a compressor with a series of rotating and rotor stator cavities, meaning that you have one disc rotating and the one is steady. And so the interest, the engineering purpose here is to improve the heat transfer for cooling the blades which rotate in the compressor. And so there is a very important challenge to improve performance of the turbo machinery, because if you increase the combustion chamber and so in the compressor, you increase the performance of the turbo machinery. So there is an engineering need to understand how the turbulence occur and how this turbulence impact the heat and mass transfer, and so the performance. But there is also some relevance in aerodynamics. External aerodynamics has a simpler configuration for investigating cross-flow instabilities. So it's typically the case where you have a swept wing. So you have the flow coming from here. Here you have a delta wing. And so as you can see on the picture, at some part above the wing, you have the development of streaks related to what they call the cross-flow instability. We come back later on the mechanism, which is due to the pressure difference in the perpendicular in the cross-flow direction here, that create a secondary flow above the wing, and which is unstable and which develop turbulence. So understanding also how this turbulence occurs above the wing, it's important also for performance, aerodynamics performance of the wing. So the boundary layer, the same mechanism takes place in the rotating boundary layer, but rotating boundary layer is much easier to investigate because you have one homogeneous direction, which is azimuthal direction, which is easier to take into account in the analytical computation with respect to the wing. So some relevance also in aerodynamics, which is maybe less unexpected. So rotating boundary layer is also a canonic flow of great interest because it is a 3D boundary layer. As you will see, the three components of the velocity are non-zero boundary layer, and there exists similarity solutions that you can derive analytically from Navier-Stokes equations. And so it's very nice to perform linear stability analysis. You can also have many diversity of complex instability behaviors as cross-flow, viscous instability, convective absolute instability, and so on. So we'll show you in the talk. It is still an open problem, in particular to when we address the question of the transition to turbulence, because if primary instabilities are very well understood, they characterize both experimentally and numerically. The question of how the flow transients to how the turbulence is triggered from this primary stability is still open. And the last point, also important for us, but it is a challenging flow, but very well suited to perform DNS, as I will show you. So what we considered in our study is not exactly the single disk configuration, because the code we had, the spectral code we had, was not really adaptive to investigating the single disk. And numerically, it's not so easy to perform direct numerical simulation of the single disk. So we considered rotating cavities, mainly two types of rotating cavities. So first, rotor stator cavity, where you have a cavity where one disk is at rest and the disk at the top is rotating. And the second kind of cavity is an open cavity with forward flow. So in this case, both disks rotate at the same speed, and we imposed radial flow here from the emitter. And as you will see in the base flow, you have two kind of Ekman boundary layers separated by quasi-solid body. rotating core. So this is also configurations which are very relevant, much relevant by the cycle disk to engineering applications. And we can show that there exists also, starting from similarity solutions developed for the cycle disk, you can also construct similarity solutions also for the cavity. So the model is incompressible Navier-Stokes equations with two main parameters: the Reynolds number, which measures the weight, the effect between viscous and the convection chair here, and the Rossby number, the ratio between the polarities and the non-linear terms. So you have these two parameters, but you have different. They can take different forms depending on the phenomenon that you want to investigate. I will not detail all the parameters and all the expression you can find in literature, but maybe the most relevant are the local parameters. You are interested by the stability, because as I told you, the stability depends on the radius where you are. And so you can construct local Reynolds number directly based on the local radius and the characteristic viscous wavelength, which is the ratio between the rotation rate and the viscosity. And we can also construct a Rossby number, which is simply the measure between the speed of the rotation rate of the fluid above the disk with respect to the rotation of the disk. Okay? And so they can take different form. Also, maybe a parameter which is important is this one for the cavities, which is h. We measure the height distance between the disk with respect to this viscous length, because depending on the value of the Reynolds number, you can have a merging of the boundary layers. It's not in the scope of this topic. So we are in the case where the rotation is sufficiently high to have two separated and relatively independent boundary layers, as we are interested by investigating boundary layers. And so I will also use, for technical reasons, this kind of rotation rate, because it's a general expression which can allow us to use this term for all configurations. So omega F between the rotation speed of the fluid and omega V, the rotation speed of the disk. So just for technical convenience. So now the base flow. The similarity solutions. So with the famous picture showing what's called the Eggman pumping. In fact, when you put the disk in rotation in the fluid at rest, by the viscous stress and the centrifugal force, the fluid is pulled out the external radius. Okay, so you have a component, radial component of the velocity in this direction. So you have also, due to the rotation of the disk, an azimuthal component of the velocity. And by continuity, in fact, to feed the boundary layers, we generate this outflow to the external radius. You have a non-zero axial component of the fluid, so W, where feeding from the core all along the radius, the flow that comes from the core to feed the boundary layer. So the idea to develop similarity solutions is to assume that these profiles are only dependent on the Z coordinates, and then you are looking for a solution on the form of omega R, which is the local speed of the disk, multiplied by a function which is only dependent on Z, made dimensionless by the characteristics delta. So if you use Reynolds decomposition and you separate the mean flow to the fluctuations, you can inject component in the Navier-Stokes equation, linearize around this mean flow, and then you obtain the partial differential equation, Navier-Stokes equation, transformed in the system of ordinary differential equation that you can easily solve depending the configuration we are, even numerically or analytically. Okay, so this is the profile that you obtain when you derive this similarity solution. So first, configuration is what you call the von-Karman boundary layer. So we have three typical configurations. One, the fluid is rotating the disk is rotating and the fluid is at rest, the von Karman monolayer, so omega d different from 0, F equals 0, corresponds to Rossby number -1. And then you have this kind of profile where you can see that you have the variation of profile of with Z. The profile of the radial component here, which is positive, and the W, which is negative, because it means that you pump the fluid from the core to the boundary layer to ensure the continuity and the conservation of the mass flow rate. Overconfiguration in the Bodovat boundary layer. In this case, the disk is at rest, and this is the fluid which rotates above the fluid. So omega d in this case is equal to 0, omega f is different from 0. Rossby equal to 1, and we have also the variation of the local parameter control of the radius. So in this case, you see the radial component of the velocity is negative because due to the pressure difference, the flow is now centripetal, so it comes from the outside to the center of the cavity. And then, in opposite to the von Karman boundary layer, also by continuity, you have in this case ejection of flow from the boundary layer to the core to maintain a constant mass flow rate within the boundary layer. What you observe also, and we'll come back later on the main mechanism for instability, is the occurrence of several inflection points in the profile, which will be the mechanism for cross-flow instability. In the cavity, where we can show also analytically, relatively easy, but you can merge these two former similarity solutions to have a similarity solution for the cavity, matching the two solutions by again by ensuring the conservation of the mass flow rate in the cavity. And so you obtain this kind of profile. So you see you have two boundary layers here on the stator, here on the rotor, and these two boundary layers, also in this case, are separated by a quasi-geostrophic core. Quasi-geostrophic meaning that you have in this region, viscous effects are very, very small. And so you can get a balance between the Coriolis force and the pressure gradient. Okay. And so you have in this, also in this case, this region here two kind of very close to Ekman layer. So the problem is that when you are doing theory, you are in infinite configuration, so everything works well. But when you are considering closed cavity, you have finite radius effect, and so the self-similar solution collapse close to the M1. For example, here if you close the so here it's open, okay? But you are even here, which is open, you have at least numerically the impact of inflow and outflow boundary conditions. But here it's closed cavity, so when you arrive close to the M1 here, the shaft around the cavity, which close the cavity, the solution collapse and you are out of the theory, and so it's a difficulty of the problem. Okay, now so in terms of instability, what is important? So first, if you are considering local linear stability analysis, you can see here, for example, from experiments, again, it's a picture from above, but you have different patterns occurring in the boundary layer above the disk. You have the first kind of patterns which are quite axisymmetric angular structures, which can be steady or unsteady in the boundary layer. And you can have also spiral arms, as seen on the first picture. So as you are the similarity solution, von Karman, Bodvad, or Ekman, suppose you can make a local linear stability analysis of this profile by making, as we call, development in normal modes, where you assume you are looking for solutions which express in the spectral space as spectral modes and wavelength KR, which is the wave number in the radial direction. Beta is the wavelength in the azimuthal direction, omega is the temporal wave. And then when you inject this solution in the problem, you derive a diffraction solution, where you are looking for K, beta, omega as a function of the control parameter, which are here, the Reynolds and the Rossby number. And so the flow will be set locally unstable if there exists a maximum wave number such that the imaginary part of the growth rate for this wave number and the set of parameters you have is exquisite. You create the temporal analysis and you can do the same for the question analysis. So while you are doing that, we found there are two types of instability. The first one, which is called type 1, is just comes from ESerre. So the first instability which has been discovered in this configuration. So it's type 1. So it's in frictional nature. So it's related to frictional points in the course flow component of the velocity profile. And then you have also the type 2 instabilities. Second main important instability occurring in the boundary layer, which is a viscous instability, which occurs when you have a combined effect between viscous stress, Coriolis force, and curvature, stringwise curvature. So this is experimental picture. If you look at here, DNS result, just to show you what happens in the meridian plane. And so here you are in the meridian plane. So here is the radius, here the rotating disk at the top. You see here an annular cavity. And then you have these patterns in the azimuthal plane, takes the form of rolls in the boundary layer. So here it is just the fluctuations of the axial component of the velocity. Why we use this quantity? Because it's non-zero, but it's rather small. So it's a good way to emphasize these vortices. And so you are traveling between the probable vortices. So in the centrifugal direction, so move to the external of the largest radius to the smallest radius in the bottom layer. Then they go up along the inner wall and develop in the rotating disk. Well, okay. It's also important, so local linear stability analysis, it's a good starting point to investigate rotating boundary layer, but it's not enough. What we did also is what we call local linear convective absolute stability analysis. So it's a concept which has been developed in the frame of open flows. And the idea is to follow the dynamics of the wave packets occurring as a response to gradually localized perturbation. So the idea is that you introduce at what point in the boundary layer perturbation, and to examine, follow the wave packet which is created by this perturbation within the flow. So three cases appear. The flow is stable, so even with a perturbation that the wave packet vanishes very rapidly and you have nothing. You can have a flow which is locally convective and stable. What it means indeed that the wave packets, due to the perturbation, grow exponentially, but it is advected faster than it grows. Okay, so this is this picture. Okay, so the wave packet grows. You will see the picture later, but it is advected, and at the end, if the time is sufficiently large, the flow come back to stability. And the last situation is the absolute instability. Then here, the perturbation grows, but it grows faster than it is advected. And so at the end, the whole boundary layer is unstable, even at large time. So this idea was introduced by Briggs in plasma physics in 1964. And it was made became very popular in fluid mechanics by the works of ESerre, Mankiewicz at EPFL, and Schomas at Athletics. We will see that this concept, which is rigorously developed for open flows, can be also relevant for the configuration we have, even if we are a bit out the scope of the theoretical framework. Example from DNS. For example, we come back to the cavity with workflow. So This is the meridian plane. So we impose that the entrance non-profile. So you see the two thin boundary layers. So the two disks will take at the same speed. And we construct a clean perturbation. So numerically, it's so easy. So the idea to model this bump, in fact, which is a model of roughness that appear in the experiment, we consider a potential flow that you can derive analytically around the cylinder. Okay? This is the expression of the analytical flow that you can derive. And then you superimpose on the boundary conditions this kind of profile to model this bump. And so the control parameter of the perturbation, so sorry, the screen is not so good. The parameter is RP here, which governs the amplitude of the perturbations, which here directly related to the diameter here, to the radius of the bump. So you can control the intensity of the perturbation depending if you are interested by a linear response or non-linear response of the. Yeah.
Here the perturbation content, the harmonic content of the perturbation is probably important, where the absolute stability.
Yeah.
You tune that because you can have an enormous variety of choices as to.
Yeah, the idea was really to model roughness in experiments, local roughness.
So those absolute stability analysis, it probably depends on the harmonic content that you put.
It only depends on the amplitude of the perturbation if you are interested by linear or non-linear response. But the nature, the convective amplitude nature does not depend on the perturbation. The only thing is that the perturbation is localized in space and in time. It's just a pulse. Like you can use also jet of air, for example, on the disk. You perturb here and you look at the response of the flow due to the perturbation. And this is here the spatiotemporal diagram, where here the perturbation is at one time. Here this is the time. Here this is the radius. So here we are on the case where the boundary layer is convectively unstable. So you see that the wave packet grows, the amplitude grows, and it becomes red. But it is advected by the mean flow, and so at the end, so here it starts to decrease, and if you continue the perturbation, you come back to the initial state, which was the state. And so to characterize also the nature of the wave packet, you can do a 2D FFT of this spatiotemporal diagram, and you extract the group velocity because it's greater. It's one of the property of absolute instabilities, instability with zero group velocity. And so here is not the case, non-zero group velocity. So we are well in the case where the flow is only convectively unstable. So now, if you increase your control parameter, so the flow becomes stable, we are looking now at absolute instability as a response of the same perturbation. So here, what we assume that you are at the boundary layer is unstable, so the imaginary part of the growth rate is positive, and we search a particular wave number which vanishes the group velocity. And the idea is to estimate for this particular value of the wave number the sign of the corresponding imaginary part of the growth rate. And so the absolute instability in the simple way, because they are behind a lot of mathematics, not at all expert and not very easy mathematics to derive this kind of concept. But it was a very nice work of ESerre and Schromas others. But we can simply characterize at the two-step absolute instability as an instability which satisfies the dispersion relation for special wave number and growth rate, with the particularity that for this set of growth rate and wave numbers, the group velocity low, and the imaginary part of the particular growth rate is positive. And in this case, you can assume that you have a positive absolute instability. So you can see the flow here, the response of the flow is different. Okay, the perturbation is here, so the packet grows, but it expands. This is the radius, time. So the packets expand larger than it is ejected outward. Okay, so this is the sign of absolute instability. And you should evaluate from this 2D plots the group velocity by the FFT. And you can see that in this case, the group velocity is well 0, so you are absolutely unstable. Locally, absolutely unstable. It's important to keep in mind, so local, linear, convective, and absolute. Okay, so local is nice when the flow is homogeneous, but it's not the case in the rotating disk, because it got a radial inhomogeneity of the boundary layer. And so you cannot only consider local tool to investigate the stability of the flow, because, and this is the core of the topic, because if there is an agreement on local ingredients and local characteristics of the stability, there is no agreement in general in terms of global behavior of the boundary layer, because, as we see, it depends on many other parameters that we define later. Okay, so now we need to define global stability analysis. When you define global stability analysis, first, global linear concept, we need to be in the weakly nonlinear assumption. It means that you have the radial inhomogeneity of the flow, but the inhomogeneity is moderate. Okay? So we assume that capital X varies as a radius, but with a small parameter, which is epsilon. And epsilon is the ratio between two lengths. It's the characteristic wavelength of the stability and the characteristic length of the spatial evolution. So here, on the rotating boundary layer, which can be scaled again with the viscous characteristic length delta, d delta, and we assume that this parameter is 4. So now, on contrary to before, when we are locally at one radius, we are looking for wave number and growth rate, G, global growth rate and global wave number, which are a function which are more local, which are depending on this parameter S, with the growth rate and the spatial coordinate X satisfying. Here, there is no. So group velocity equal to 0. Variation in space of the growth rate, so here it's XS equal to 0. And the imaginary part of the growth rate positive. So Schomas in 91 demonstrated that to have a locally, to have a flow which is linearly, globally unstable, you need a locally absolutely unstable region in the boundary layer. It is necessary condition, but it's not enough. If you want the sufficient condition, you need to introduce nonlinearities in your analysis. And the nonlinear global mode, this is what appears in the boundary layer. It's characterized by a steep front, and I will show you later what we have. A particular case which is relevant in boundary layers is what Pierre and Muir named the elephant mode. Is a kind of a global mode embedded. So global mode developing in an absolute region and embedded in two convective areas of the stability. So here it's convectively unstable. Here you are in the region of absolutely unstable, or you have the front, the global front which develops. It corresponds to the spiral arms that you have seen experimentally on the picture. And then you have behind another convective area, but the boundary layer is not stable. What is interesting with this characteristic of this front is that it is nonlinear, so you need to have a very strong perturbation, strong amplitude perturbation to produce it, but it is completely determined by local linear ingredients. In the sense that the steep front here occurs at least theoretically, but it works well in DNS, you can see. It occurs at a radius corresponding to the transition convective and absolute instability, determined linearly and locally. Okay. And the growth rate here, if you measure the slope of the front here, is a growth rate provided by the local linear absolute instability. But the front globally is a non-linear mode. Scenario of transition to turbulence now. So I gave you now the main ingredients you need to understand, the main mechanism you need to understand what happens in the transition process to turbulent in rotating boundary layer. Okay. So from theory, in fact, there are two main scenarios that can be expected. And the key point in these two scenarios is a competition between the inhomogeneity of the flow, which has a stabilizing effect, and the non-linearity of the flow, which is a destabilizing effect. And both phenomena occurs in finite size system. And so you cannot restrict your investigation of local stability analysis. You need nonlinear global analysis. So here you have competition between two scenarios. One, which is named absolute dominated. It's a case where you are able to produce first a local linear stability and absolute stability. And this absolute instability, so this is spiral arms we have seen in the experimental view, becomes itself absolutely unstable to secondary instability, which is even more unstable than the primary instability. And then you have, see the result, you have first mode related to this absolute instability. And when this mode is saturated, you have a secondary float occurring on the back of the first front. And then the nonlinear interaction between these two modes leads to turbulence. So in this case, at least from a theoretical point of view, in the paper I gave you here, you have nonlinearity, which is taken into account because it's key ingredients, but all the work here is done in parallel assumptions. So you have not taken into account inhomogeneity of the flow. Now, the second type of scenario is the one based on convective dominated instability. So it occurs generally in the cleaner environment because you need to have a very no perturbation to be sure to not produce rapidly instability. So it was observed experimentally by Open and Cork in 2006, and it can be also reproduced theoretically using linear global stability, but only when you are in the assumption of linearity. So you see that in these two scenarios, you don't mix the two mechanisms which compete, the non-linearity, the non-homogeneity. So for that again, so yeah, explanation that details in this scenario. So to get the scenario absolutely dominated, you need a region of absolute instability in the sense of local linear stability analysis before the radius. If the radius of the cavity or the disk is too small to have this unstable region in the configuration, you will see nothing. But if assume that the radius is sufficiently large and that you have an absolute stability region, you can have this first mode growing in this region, and then with the secondary floats. And the secondary float, you have two types of bifurcation that you can observe. The first one is supercritical bifurcations, which is driven by a linear global mode. Already see the results from the slide. So you need something which excites the flow to bifurcate on the unstable flow. And typically, it is the edge of the cavity. So this is the finite size effect of the cavity which generates this edge global mode, which leads to the global mode of the boundary layer. Or it can be subcritical, and in this case, this is a response to a strong amplitude perturbation. In the case where the flow is assumed to be dominated by the convective modes, the flow in this case acts as an amplifier, so you need small perturbation, which is amplified. And you need to assume, in this case, that the radius of the cavity is large enough to the packet saturates before it is ejected out of the cavity. And this is, you have convective modes traveling in the cavity. They saturate before the outflow. And as they saturate by nonlinearity, they become itself absolutely unstable to the secondary instability, and then you have transition to turbulence. In terms of picture, so this is a sketch here of what appears. So you have a kind of absolute scenario. So it's what we have seen on the picture at the beginning. So you have quality of the picture. Sorry. So you have spiral arms developing, and then behind here you have lines of turbulence. So it's absolute instability related to spiral, and then secondary modes and interaction to trigger turbulence. When you are convective scenario, so it means that you need to introduce a C perturbation. This is roughness put on the disk, roughness put on the disk at local values. And depending on the intensity and the amplitude of the perturbation, then you can trigger turbulence more or less faster, depending on the amplitude of the initial perturbation. What I said before, so the value of the critical value of the Reynolds number here depends on the amplitude of the initial perturbation. You can see that we have here small perturbations, so the packet grows exponentially, travels, it grows, but at the end it saturates and then becomes absolutely unstable and transients to turbulence. If the amplitude is stronger, so you go faster to the saturated state, and then you transient to trigger turbulence before in terms of Reynolds number. Now come back to DNS. Study. So again, first on the rotating cavity with flow. So you introduce the perturbation flow, the 2-3 parameters, which are the rotation of the disk and the mass flux rates, which is imposed at the plants. And locally, you have 2 parameters, the Reynolds number and the Rossby number. So we use the perturbation mimicking the roughness at the wall. The code is a 3D spectral DNS, Chebyshev Fourier for cylindrical Navier-Stokes equations. And we made the computation over sector only of the cavity to power 68, because 68 is known from methodological analysis to be the most unstable mode, the most absolutely unstable mode for the range of parameters we have. So we concentrate on a very narrow sector to be more efficient numerically. And as we are interested by simulating convective optimal scenario, as you are any point in simulation noise, due to the imperfect matching, I would say, with the boundary condition, because the difficulty, the numerical difficulty when you have open flow is to impose the boundary condition here and at the outflow. At the inflow, we have the similarity solution, but the similarity solution, so this is the 2 Ekman layers and the joystick core, it's a linear solution. And since the flow is very sensitive to any small perturbation, you cannot avoid even small perturbation propagating in loop. So if you don't want that convective mode develop, you need to filter these modes. And a very efficient way, you cannot, these modes are, unfortunately, anti-symmetric. So you cannot filter them in the Fourier space, because it's too easy. So we need to filter them in time. And what we use is the technique which it's called the selective frequency damping, which is a kind of strong penalization here, where you kill all axisymmetric modes that would like to develop in the flow. And it's very high just to keep only the absolutely mode that we want to make in the perturbation. First, what we found is that the flow is globally linearly stable, but non-linearly unstable. What it means that depending the amplitude, so you are, the parameter you control is the amplitude of the perturbation, so the size of the roughness that you can have in experiments. Okay, so if you have you consider a perturbation very low amplitude, for example, here is 8⁻³ you generate a perturbation, so you generate a packet. So here's the amplitude growth. But around the middle of the cavity, the packet stops growing, and then the amplitude decrease, and this curve is amplified 10 times to see something. So the linear response of the flow, so in terms of linear response, the flow is stable because at the end you have no flow. I will explain you why we have this linear stability. Now, if you consider a 10 times larger perturbation, so 8⁻², then you have the same growing the amplitude of the wave packet, slight decrease, but you keep some unstable mode in the cavity. So this is in the sense that if the perturbation is small amplitude, the flow is globally linearly stable, but you can have unstable flow if you consider large amplitude. Why, when you have, why the flow is globally linearly stable? In fact, it's due to homogeneity, the stabilizing effect, and it's what people call detuning. Detuning is this phenomenon that you can test numerically. So what we have done, we have considered a cavity, and we have a different radial locations. Here you have performed local linear stability analysis. So what we are doing is that we pick up the profile at one radius, and we copy the profile at all values, so to create an artificial parallel flow in the cavity, and we fix we avoid interaction with an equal to 0 mode, and we disturb, and we have the locally selected case. So we are able to we are doing a linear stability analysis, and we extract from this simulation the max wave number, the most critical wave number corresponding to absolute instability. And here, this is in the non-homogeneous flow, the evolution of the packet of the instability wave number when the packet travels in the cavity. And in fact, you can see that the gap between the theoretical value and the measure value grows when you flow outside. It means that you are further and further from the most critical condition in the flow. What explains that at the end, the flow will stabilize when the perturbation is too small. It's due to non-homogeneity. And you can see here, again, it's like before. So you have the amplitude of the wave packet, and then the decrease on the packet reach the outflow. So now, come back to the nonlinear instability, nonlinear globally instability. Okay, so we consider now a strong perturbation, again with the cavities, and we are filtered. So we are in the 1 pi/68 mode, so we have only one mode, so 68 spiral here, you can see from the top. And when you are looking at the spatial temporal diagram, then you see what we call the global mode. Means that we have an unstable mode which takes place in a large part of the cavity. So just the response of a localized in time and in space perturbation, but with strong amplitude. And this front is, as expected by theory, located at the Reynolds, so at the radius, local Reynolds number, exactly corresponding to what is expected by theory from the transition to convective absolute instability. Okay, so this is the view from the top, and here you have the energy which is in the mode to show that it is a steep front. This is a global mode, nonlinear global mode, characterized by a steep front. So the steep front means that you have a strong increase here of the energy, an exponential growth. And if you measure the slope, at the border, you see here you are convective, here you are fluid, here this is the local region. But the front is really located as expected by theory at the transition between convective and fluid instability, and the growth rate of the front is perfectly given by the linear stability analysis results. Now this is just the front of an elephant mode, because here so you have saturation here, but the cavity in this former computation was too short, so no turbulence behind. So now what's happened when I consider a larger cavity? And this is what you have. It's like an experiment. The same spatiotemporal, so the global mode here. And just behind, you have a secondary float, which is plotted by the black line, and the turbulence behind. So when you look at here, what happens? Again, you have the plane. You are here. This secondary float is much less investigated because such kind of computation requires quite a lot higher resolutions. It's quite expensive, but so this front, it's still an open question. What's the mechanism related to the secondary instability which induces the secondary front? But what is clear is that here we have a secondary front and we have behind something which is incipient turbulence. It's very clear here. This is a meridian view of the cavity, where you have so the half height of the cavity, and so you have vortices which invites this is the whole cavity, because when the boundary layer becomes turbulent, they become much. Here also, this is the representation of the frequencies with the radius showing that you have a bursting of all frequencies, so characteristic of turbulence just after the secondary front. So we have this kind of view. So this is a full 3D view by DNS. So here the 2D, this is half height of the cavity. So here we have here. You have the stable, so you disturb on here, stable layer. So packet grows. Saturate. So you have here the spiral corresponding here to the global nonlinear modes and the turbulence, and you see that the boundary layer is now fully turbulent, with vortices expanding the whole height of the cavity. Okay, so we have three positions: the position of the primary front, which has all the characteristics of the elephant mode, predicted by theory, the secondary front, and then the turbulence. So in this case, but everything has been done to observe the scenario, because we have filter, we are counting the 68 cavity factor. So we are able to reproduce by DNS a scenario based on the cascade of absolute modes as predicted by theory. And it was observed previously only on the envelope equation by Quero and Chomas, and for the first time in simulation by DNS. Okay. So if we consider partial conclusion of simulation, so we have linear and nonlinear mechanism which compete to transient to turbulence. The second point, I don't remember which it was. The third point is that the boundary layer is locally absolutely stable. It's locally absolutely unstable, globally linearly stable, and globally non-linearly unstable. And why? Because you have detuning due to non-homogeneity. You can stop convective modes growing and avoid transition. So in control condition, because everything has been done again to get this result, the scenario predicted theoretically by Lingwood is clear, based on local absolute instability, global nonlinear modes, secondary instability, shown yes. In this case, this scenario, this transition is called subcritical, because we are doing a very high amplitude perturbation to get subcritical simulations or large amplitude perturbation triggers the mode. So the question that we can ask, what happens in the flow configuration with less artificial control? Because I explained here, everything has been controlled to obtain the scenario. The characteristic of the global mode match the theory is slightly different from experiments. Why? Because in experiments, as you have seen, but you observe this kind of global mode and turbulence. But when you look measurements, the growth rate of the non-linear global mode is much smaller than expected by Theorie and by DNS in the sector. So to understand this, a few years later, we perform new DNS, but in this case, to avoid any control required by OpenFlow, we perform DNS in a rotor-stator cavity, closed rotor-stator cavity, cylindrical one. So it means this is a boîte à camembert here. So we have rotating disk at the top, stationary disk at the bottom, and the stationary stator. Alors, in this case, the difficulty is that the border boundary layer, which is the other kind of boundary layer, is very unstable. So very rapidly, when you start simulation to increase rotation of the disk, you have instability in the border layer. So it's not interesting. I would say it's quite difficult to investigate because everything occurs very fast, and so you cannot distinguish properly the mechanism that you can see on the rotating disk. But you have traveling vortices, and what is nice with the cylindrical cavity is that as you decrease the Reynolds number, the radius, in fact, you are sure that you have a region here where all perturbations are damped because it's very stable, because you have very small radius. Okay, so even if you have a lot of perturbation growing in the very unstable bottom layer, no perturbation is expected to arrive at the top because it's damp. It's very smooth region around the axis. So the flow go up here on the bottom layer, and here we have the carbon boundary layer. Okay, so when you increase, this is the view that you have now. So you have a stator with instability. And then you have the global modes and incipient turbulence at the border of the cavity. Alors, if you look at now all the stories, the story is performing DNS and step by step the rotation. What is nice is that the rotation is only a parameter you have, okay? Because you have no flux, everything is closed, the boundary conditions are well defined, and so on. So what you observe first is a first spiral occurring very, very soon at the border. And you are going to see that this mode is driven by the edge. In fact, it's not the boundary layer modes. It's a mode which is due to the return here of the flow between, because here you have a relatively strong jet coming from the outflow boundary condition, boundary layer, which impact the steady wall. Okay, so you have a strong jet impacting the wall with some curvature effect. So you have many kind of instabilities here that can occur due to the curvature, due to the vertical boundary layer also which develops. So you have a kind of permanent noise, I would say here, generated by this edge condition, which are able to produce some spiral, and then step by step, you see that the spiral invade more and more the radius of the cavity, and we are looking now at the characteristic terms of wave number. So you have first the primary mode, so only states that it's equal 82 spiral driven by the edge. Here we see the curve given by the local stability analysis, local linear stability analysis for absolute instability. So you see that at the beginning of the simulation, the front is far in the convective area region in the sense of local stability analysis. And step by step, increasing rotation, then the simulation with the front, like before in the flow cavity, which is more or less located at the convective absolute transition, as expected by the non-linear term. Okay. And what is interesting by DNS, so here is the full cavity, no sector, so 2 pi in the azimuthal direction. So we are able to separate all modes and see how the mode grows independently, I would say. And so here you have the most selective, the most intense modes in azimuth. Okay, so the most energetic mode clearly determines the slope of the sea front. So here, this is the sum of all the energy corresponding to all modes. And each azimuthal modes exhibit a steep front, as previously in the fourth locality, with a spatial growth rate in agreement with local linear stability analysis for local absolute instability. So if you compare the location and the growth rate for each mode, it matches very well the result given by local linear stability analysis. But as you are at the simulation is non-linear, so you have interaction and the full solution, which is solve for all modes, is the black line, black line. And the total energy, this sign, presents a smoother growth rate of each mode taken separately, since the energy of each mode starts growing at various radial locations. So when you sum with this mode, you have this kind of result. And which is very nice, is that the growth rate, when you measure the slope of its front, which is less steep than previously, it is in very good agreement with what we observe in experiment. Okay. So each mode take independently, you match the local linear stability result previously, because previous simulation, we have only one mode, and the harmony is 68. In this case, you have all modes. But you explain here why in experiment they observe a smaller growth rate, because it is simply the results of nonlinear interaction between absolute mode. Okay, so to conclude, we have investigated with turbulence in locating these boundary layers of two cavities using spectral DNS and linear stability analysis. You have seen that there exist multiple scenarios based either on convective or absolute instabilities, which take from traveling circular patterns. What the study underlines and confirms the competition between inhomogeneity stabilizing and nonlinearity destabilizing, but also the role of the forcing that you impose in the simulation, and the impact also of panel size effect when you are in the real world comparing to experiments. So the discrepancy observed between the global linear and nonlinear dynamics, so why we are able to observe these two scenarios, it's mainly induced because before arriving in the absolute region, we have a very large convectively unstable region upstream. And then depending the noise you have in this region, you can amplify or not perturbation before the absolute instability. So if you are in clean environments, so I would say kind of artificial environment, because I think in real life it's cannot be so clean, then we are able to observe an absolute scenario with two kind of scenarios, subcritical based on subcritical bifurcation or the supercritical bifurcation. So the subcritical, because you need something that is driven by the edge to perturb, to disturb, generate instability, and subcritical because you need, if you don't have edge effect, very strong amplitude to disturb the flow and get the convective scenario, which have not been observed, not been investigated, I would say, need a strong forcing and a large extent for the convectively unstable non-linear effect. And you understand that if you have a flow, you disturb it, so you generate a wave packet which travels. It can grow, but if you have not enough space to saturate, you cannot lead to turbulence. So it seems, however, realistic in real configurations, because in real configuration, you cannot avoid the roughness of the disk or vibration of the disk and so on. So you have strong noise. And so the last point is to say that some work to do, in particular to investigate the nature of the mechanism related to the second instability, just before the turbulence. Okay, thank you very much.